Hello, student. Welcome back to this topic of fiber optics. And in this session, I am going to explain what is this mode of propagation, or it is also called as the V number. Even though the light rays enter the fiber with angles within the acceptance angle, it does not mean that all the rays will have a sustained propagation. Only certain rays will have some modes of propagation. These modes of propagation depends upon the diameter of the fiber, refractive index of core and cladding, and the wavelength of the incident rays. So a parameter which indicates the number of modes of propagation is called as the V number. Therefore, it is given by V equals phi d divided by lambda into root of n1 square minus n2 square. So actually this parameter indicates the numerical aperture. Instead of writing this, you can also write the numerical aperture here, NA. You can write NA here. So this is such a number called as the V number. So that indicates the modes of propagation of the light rays inside the optical fiber. All the rays will not sustain their propagation inside the optical fiber. Only few rays sustain their propagation inside the optical fibers. So in this equation, this d is the core diameter, and lambda is the wavelength of the rays, and n1 is the refractive index of the core, and n2 is the refractive index of the cladding. So if the fiber is surrounded by a medium of refractive index n0, then the above expression becomes V equals n0 phi d upon lambda into root of n1 square minus n2 square. So it is very clear that this V number depends upon, is directly proportional to, the V number is directly proportional to the numerical aperture, and it is directly proportional to the diameter of the optical fiber, and also it depends upon the surrounding medium, and inversely proportional to the wavelength of the light ray which is entering the optical fiber. So for the V number very greater than 1, the number of modes supported by the fiber is given by the number of modes is equal to V square by 2. And here is the comparison of SMF and MMF. SMF means the single mode fiber, and MMF means the multi-mode fiber. So we are comparing the features of single mode fiber and multi-mode fiber. So the first parameter is the core size. So the core size of the SMF means single mode fiber is ranging from 7.5 to 10 micrometer, whereas that MMF is having 10 to 100 micrometer. And numerical aperture, here it is 0.1 to 0.12, and here it is 0.2 to 0.3. And refractive index, here it takes a step, and here it takes a step as well as the graded variation. And attenuation is which is in dB per kilometer. It extends from 0.25 to 0.5, but here it extends from 0.5 to 4.0. So it is very clear that the attenuation in case of SMF is small as compared to the attenuation of MMF. And information carrying capacity in terms of distance for SMF, it is very large, but it is small to medium range. And the usage, long haul carriers, CATV and CCTV are the usage or the applications, and short haul, for example, LAN network for LAN network MMF are used. And the preferable distance for deploying the cable is, here it is over 2 kilometer, but here it is under 2 kilometer. And splicing, that means the task of connecting the two fiber is called as the splicing. And splicing in case of SMF is very difficult, whereas the splicing in case of MMF is easy. So these are the comparative features of SMF and MMF. Next, we'll discuss what is this attenuation. As the light propagates through an optical fiber, it suffers a loss of amplitude and change in shape. The loss of amplitude is known as attenuation, and the change of shape is called as the distortion. There are three mechanisms through which light attenuation takes place. They are absorption losses, scattering losses, and radiation losses. So we'll see these three losses one by one. So first one, absorption losses. There are two types of absorption losses. One is the absorption by impurity, and the other one is the intrinsic absorption. So we'll see what is this absorption by impurity. The type of impurities that are generally present in the fiberglass or transition metal ions, such as iron, chromium, cobalt, and copper. During signal propagation, when photons interact with these impurities, the electrons in the impurities absorb the photon's energy and gets excited to the higher energy level. So within very short time, they will come down to the lower energy levels by giving up their energy in the form of photon, which have different wavelengths and phase with respect to the signal. So on interaction of these, that means two photons are there. Now the incoming photon, light energy, and the energy emitted by excitation and de-excitation of these electrons in the impurity atoms. So these two interact with each other, and some energy of signal is lost because their phase will be in different directions. Because of that reason, the signal loss takes place. Even some hydroxyl groups or ions enter the fiber material during its propagation. This also causes absorption losses. So the second one is the intrinsic absorption. The fiber itself as a material has tendency to absorb the light energy. However small it may be, and is called as the intrinsic absorption. That means the absorption of light energy by the material of the optical fiber itself is called as the intrinsic absorption. The strong electronic absorption occurs at UV wavelengths, while Vibrational absorption occurs at higher wavelengths up to 7 to 12 micrometer. The absorption of loss does not only occurs at a fixed wavelength, but occurs over a broad band that extends up to the visible part of the spectrum, with the losses decreasing as the wavelength increases. That means uh, higher wavelength radiations will have the lower losses and vice versa. So next we'll go to the scattering losses. Scattering losses can be grouped into two categories, that is the release scattering and other type of scattering. First we'll see what is this relay scattering. While the signal travels in the fiber, the photons may be scattered because of sharp changes in refractive index values inside the glass over distances that are small compared to the wavelength of the light. This type of scattering is known as the leg scattering. So the leg scattering is inversely proportional to the fourth power of the wavelength, which means that light of smaller wavelengths are scattered very efficiently. A scattered photon moves in random directions and in all probabilities. So these scattered photons, get interacted with the incoming uh, signal photons, and that leads to the loss of signal intensity. The sharp variation in refractive index value inside the fiber is induced by localized structural inhomogeneities in the material during fabrication. In addition to that, the presence of oxides such as SiO2, silicon oxide, and GeO2, P2O5 results in a rapid fluctuation of composition and hence refractive index. So the other type of scattering losses are due to the structural inhomogeneities and defects created during the fiber fabrication. These defects may be in the form of trapped gas bubbles, unreacted starting materials, and some crystallized region in the glass. But the manufacturing methods are now so efficient that these are negligibly small compared to the leg scattering losses. So I'll go to the third type of loss, that is the radiation losses. So radiation losses occur due to the bending of fiber. There are two types of bends, namely macroscopic bends and microscopic bands. So in case of macroscopic bends, this refers to bands having radii that are large compared to the fiber diameter, such as turning a fiber around a corner. Fiber can be bent with the radii of curvature as small as 10 centimeter with negligible loss. Fibers can withstand bends of curvature down to 150 times the fiber diameter. So, although the loss is negligible for small bands, it increases exponentially when the bending reaches a certain critical radius of curvature. Any bend of radius less than this threshold makes the losses suddenly becomes extremely large which indicates that the absence of total internal refraction. That means even at higher bands, the losses become so high that the total interreflection is not going to take place inside the fiber. So that leads to very huge losses in the intensity of the signal. Then I will think about the microscopic bands. So these are repetitive small scale fluctuations in the linearity of the fiber axis. So along the axis of the fiber, there can be some small fluctuations in the linearity. So that is the problem. So microscopic bends. So that fiber axis might have bend to a small level at the center of the fiber. So that leads to the microscopic bends. And microscopic bending occurs due to non-uniformities in the manufacturing of the fiber, or by non-informal lateral pressures created during the cabling of the fiber. So that is another reason, because when the cables are deployed under the ground or somewhere else, high pressure may be put over the cable. So that leads to some linearity in the fiber axis. So some irregularities are created along the axis of the fiber, leading to some loss of the signal. So these microscopic bends couple light between the various guided modes of the fiber, and some of them then leak through the fiber. That means leakage of the signal may take place, because again, when you say that the signal is leaking, the total internal reflection is not taking place inside the cable. So that is the main point. And microscopic bending losses could be minimized by excluding a compressible jacket over the fiber, which could withstand the stresses while developing the fiber. So this is a graph of attenuation versus wavelength. On the x-axis, we have plotted the wavelength of the incident light, and on the y-axis, we have the attenuation. You can see here up to 1 micrometer wavelength of the incident light, the scattering losses by scattering are more. As there here, some molecules are absorbing the energy, like H2O, it is water molecules, and hydroxyl molecules may absorb the energy, and at higher wavelengths, higher absorption takes place. So we can define this attenuation coefficients. Before that, a Lambert's law, I am going to define the Lambert's law. So this Lambert's law states that the rate of decrease of intensity of light with distance traveled in a homogeneous medium is directly proportional to the original intensity of the light. So if P is the original intensity and capital L is the distance traveled by the light in the medium, then minus dP by dL is proportional. This is a proportionality symbol, is proportional to P, the original intensity of the light. And this is minus dP by dL because the intensity of the light is going to decrease with its propagation through the cable. So you can remove this proportionality sign by putting equal to here. So it becomes dp by dl equals minus alpha into p, where alpha is now it is a proportionality constant. This is known as the attenuation coefficient, or simply as attenuation. So its value is different for different media. The negative sign indicates that intensity decreases as the distance is increased inside the fiber cable. So from equation 1, we can write dp by p is equal to minus alpha into dl. So we can integrate this equation between the limits of p is equal to p in, that is the initial intensity of the light with which the light is launched into the fiber, and p is equal to p out, the intensity of the light that emerged out of the fiber. We get, so we are integrating the equation 2. So it becomes integration from p into p out, dp by p is equal to minus alpha into integration 0 to L into dl. So it is a constant, so that is why it is kept outside the integration sign, and integration from 0 to L dl. So after integration, it becomes ln of p out p in as the integration limits is equal to minus L into A capital L, because integration of dl is L. And so here this can be written as ln of p out by p in is equal to minus alpha into L, or alpha is equal to minus 1 by L into ln of p out by p in. So in terms of decibels, the above equation becomes alpha is equal to minus 10 by L into log of p out by p in terms of decibel per kilometer. So the amount of attenuation varies with the type of cable and size. So glass has low attenuation than plastic. Wider cores have less attenuation than the narrower ones. So the attenuation is directly proportional to the length of the fiber cable. So in the next session, I am going to discuss about this distortion or dispersion. Thanks for listening.